Hey everybody, we're going to continue now into this next chapter on numerical variable inference. So looking specifically, we're really interested in an inference on the population mean. And we'll extend the ideas of inference on a single population now to what if you're comparing two different populations. And first we're going to be looking at when we're looking at two populations, or if you have two samples, the first have to kind of classify it as like if you have paired data or unpaired data. So when we say paired data or paired, paired samples, usually it's where you have a bunch of individuals and we are measuring something before or after. That's usually what it is, like before some treatment and after some treatment. Or it could be where you have kind of paired individuals, where you have, say, like a husband and wife, and you're maybe asking a question like, we're measuring, I don't know, whatever it is. Like there's a logical reason to match up these individuals from these two samples. That's that kind of thing you'll see with paired sample data. If you have independent samples, really the individuals from one sample have nothing to do with individuals in the other. Like they're not related in any way. The two sample sizes can be different. But we're not measuring individuals before and after some sort of treatment or something like that. So we'll have really with the paired data, what we're really interested in is looking at the difference for each individual. We can really just look at for each individual pair, we take the measurement from the first person and the second person, take the difference. We actually have this third set now of differences, and we would actually just do one sample inference on the differences. With two independent sets, it's a little more complicated. So let's look at paired data in more detail. So, okay, so let's look at this example. We're testing out these new wetsuits, and we're giving them to 12 competitive swimmers. Each of them is asked to swim 1,500 meters, and we're going to see if their speeds with the wetsuit and with the standard wetsuit or standard swimsuit, if there's any sort of significant difference. All right, let's on average. So what we would do, this is an example of the value, the stuff that's collected from these 12 individuals, the measurements of time, right? And what we have is the velocity, really. So the velocity was calculated with the wetsuit and with the swimsuit, and we calculate the difference. The difference is going to be the wetsuit velocity minus swimsuit velocity. And we proceed to do one sample inference on these differences. And that's just like the stuff we were doing before, T-tests and so forth. So yeah, this is just to go over you would calculate the average of your differences. That would be, we call that D bar, and we will use like the D's to be the abbreviations for all the differences. Here it's just notation. It's all just notation. So here, now this is something I have to say. We use Greek letters to represent population parameters. Here we're using the Greek letter delta to represent the difference in the population means. Which I actually haven't seen in other texts, but I like it. It makes sense to use delta because, well, delta means difference, but anyway, delta is like the mean from the one population, like the average velocity for the wetsuits minus the average velocity for the regular swimsuits, right? So if there's no difference in no significant difference, I should say, in the average velocity, that would be delta equals 0. So that's going to be our null hypothesis, that delta equals 0, that on average, the average speed, there's the average difference is 0. And then the alternative would be that the average difference is not 0. Here, a two-tailed test would just detect whether there's any significant difference between the two types of swimwear. You calculate your test statistic the same way you would for one sample t-test, because that's exactly what we're doing here, is a one sample t-test. And you calculate your p-value the same way. And you would calculate confidence intervals the same way too. It's going to be the 95% confidence interval for the difference in means, or for this delta, would be d bar, with the average of the differences, plus or minus this margin of error, and it's going to be calculated based on the, what your confidence level is, and it's based on the variability in your sample. That's the standard deviation of your differences, SD, and your sample size, so the square root of n. And of course, you can use the t-test function in R. Now here, what you can do is you could give our two vectors of numbers. You see, we give the wetsuit velocity and then the swimsuit velocity, and we say we're going to do a two-sided test, and we add this other option, paired equals true. R will do all the work. It will take the difference between the two values. It will do the one-tailed test, or the one sample test on the differences. And it's important to just remember this: the t-test, the two-sample paired t-test in R, it bases on the first vector minus the second vector. So if you're not sure like which one should be minus the other, you should be clear on that, because the function in R is always going to be the first vector minus the second vector. And the point is, if you would get the exact same results if you did a one sample t-test on the differences. So that's all of this point is to get to the point that the inference on paired data is just one sample inference on the differences. Okay. Now, suppose instead that our two samples are drawn from two independent populations. Okay, so here's a kind of motivating example. Does a change in non-dominant arm strength after resistance training differ between men and women? So what we're going to have is we're going to have a population, like a sample of men and a sample of women. They'll be doing some resistance training, and we'll see what the change in their non-dominant arm strength is. Now it looks like this is the FAM-USS data set, and it looks like let's see, we're using column here. It looks like this is just showing us a few of the rows of this, and it looks like probably the NDRM.ch is a measurement of non-dominant arm strength. So taking a look, actually, NDRM.ch, you can see the distributions of these two samples, and you can see it looks to be different. Looks to be different from the box plot. Making a side-by-side box plot is nice. Now this is a great way of creating a side-by-side box plot. You would say box plot the variable that contains your data, and then you do a squiggle, and then you say how you want to group it by, and it'll create these nicely grouped and distinct box plots on the same axis. Of course, I personally like horizontal box plots, but to each their own. So if we're interested in comparing this, the null hypothesis is going to be the mean change in arm strength for men or for females is equal to the mean for males. So mu F equals mu M. And now instead you could subtract mu M from both sides of this equation and put mu F minus mu M on the left and say equals 0. And this is actually kind of typical because so this is us saying that the null hypothesis is that the difference in the means is equal to 0. And then because all of the test statistic is going to be based on the difference of the sample means. And so that's why typically people write, or oftentimes you'll see the two parameters on one side of the equation, like mu F minus mu M. Okay, so we're interested in testing something about mu1 minus mu2 here, or mu F minus mu M in this particular case. And the point estimate for the difference in means is the difference of the sample means, x bar 1 minus x bar 2. And it's always really important to be clear about what group 1 is and what group 2 is when you're doing these, because you don't want to mix those up. So this is the test statistic. Now it looks like a little beast, and I don't want you to feel like you have to memorize this formula, but it's good to just know what's going on. So just like before, what we're doing is we're finding, this is, I guess you could say it's a z-score. It's a standardized, we're standardizing our difference in sample means. So x1 minus x2, x bar 1 minus x bar 2, that's the difference of the sample means, minus mu1 minus mu2, that's the hypothesized difference in population means. In this case, it's going to be 0 because that's what we're going to assume that in the null hypothesis, we'll assume that there is no difference in population means. And then divided by this thing on the bottom, that's the formula for the standard error. That's the standard deviation of the sampling distribution for this difference of sample means. The degrees of freedom is a little bit more complicated. There's this nasty formula. It's roughly, you can approximate the degrees of freedom using the minimum of n1 minus 1 and n2 minus 1. But there's a better approximation. In typically though, like it's not going to matter a great deal because the difference is going to be pretty minute in terms of the p-value calculated. Anyway, it's best not to be doing all of this. Now that we're at the point where you don't want to be doing all this calculation by hand. So anyway, so this degrees of freedom is important for finding your p-value and for calculating the critical t-value if you wanted to do a confidence interval for the difference in population means. But yeah, like you literally want to use software to do this for you at this point, because it's like if you just enter the formulas, there's too many opportunities for making little calculation errors. But yeah, so the idea is that we can create a 95% or whatever percent confidence interval for the difference in population means. We would say something like, I'm 95% confident that the difference in the difference in the average population averages is between this and that. It's probably the clearest way to say it. And you also want to be careful when you're interpreting these confidence intervals to not imply that the difference in population means is the random variable. So let's see. So this is how you would do a t-test, a two-sample t-test in R. The syntax, the stuff you type in, is pretty much the same as you would have for the paired. The difference is that you have let's see, you say paired equals false, as that option instead of paired equals true. So you just give it the one sample. So this is just subsetting it by the rows for females, and then you give it the second sample, which would in this case is the change in arm strength for the males, and the null hypothesis is that the difference in means is equal to 0. So that's why we put mu equals 0. That's the null hypothesis mean. And you can see it in the output. You can see this spelled out pretty clearly. So this is another thing you can do. You can use this tilde to group this this vector by this grouping variable, and because there's only two groups, it'll do the t-test really nicely. Yep. So here, if we had done the swimsuit test using unpaired test, what you'd actually find is that the p-value is much higher. See, this is 0.1849 compared to the using the paired test. You get a p-value that's quite different. That's 0.000008. That's like almost nothing. So here you would say there's very clear evidence that the average so let's see what the best way to say it. There's very strong evidence from the data to conclude that the average change in swim velocity is not 0, or which is to say that there is a significant difference in average swim velocity for these two types of swim sets or swimming outfits. However, if you compared them as independent samples, you get a much higher p-value, and you would not make that conclusion. So generally speaking, if you a paired t-test is going to be much more powerful than a independent sample t-test. But of course, you can only do a paired sample t-test if that's the way the experiment has been designed. If you actually can pair up individuals one by one because of the way the data is structured. But yeah, so the power of a test is essentially how well it's able to detect real differences in the populations. So the power is, if the null hypothesis is false, what's the probability we reject the null hypothesis? So a more powerful test is going to be better at rejecting the null hypotheses that are false. That's what power is. Oh, let's talk about power and sample size. So we'll get into power a little bit more in more depth. So the power of a statistical test. It's the probability that the test will reject the null hypothesis when the alternative hypothesis is true. In other words, it's the probability of correctly rejecting the null hypothesis, and so if you recall, a type 1 error is the probability of incorrectly rejecting the null hypothesis. That's when the null hypothesis is true, the probability that you reject it anyway. That's the probability of making a type 1 error. So the power is going to be, the power of the test is depending on the effect size, which is really how different are the two population means. It also depends on the standard deviation of the two populations, and it depends on the sample size. So usually by you can change the sample size to make the test more powerful. And generally, the larger the sample size is, the more powerful your test is going to be. Now I mentioned type 1 error. This is a great table showing you kind of what can happen at the end of doing a hypothesis test, right? In reality, the null hypothesis is either true or the alternative hypothesis is true. Now, if the null hypothesis is true and you don't reject the null hypothesis, you've made the right decision, and that's what you call a true negative. So you didn't reject the null hypothesis, you're sticking with it. There's not enough evidence to suggest the alternative, to like support the alternative hypothesis. That's a correct decision. Your decision is in line with reality. Now, if the alternative hypothesis is true, the right thing to do would be to reject the null hypothesis. And now, the probability when the null hypothesis is true, the probability that we are going to reject it and make it what's called a type 1 error is alpha. So we set alpha to be a value that we're comfortable with. That's the significance level. So we can say, if the null hypothesis is true, how willing am I to make the decision of rejecting it, even though it's true? And you set that out to be alpha, like 0.05 or 0.01 or something. Now, on the other side, if the null hypothesis is false, the probability that I don't reject it is beta. That's the flip side of things. And so what we have here is beta, or actually 1 minus beta. That's the probability of rejecting the null hypothesis when the null hypothesis is false. That's called power. 1 minus beta is power. And the probability of a type 2 error when the alternative is true, that's this beta. Now, generally, you kind of have to choose, do you want alpha to be lower or do you want beta to be lower? The only way to drive both of those down is to just increase the sample size, or to use a more clever test method. But really, the test methods that we're using are the best methods around. So at that point, we just have to increase sample size if you want to bring those down. We're going to explore these in one of the labs and just see how you can control the rate, the likelihood of making a type 1 error by changing your alpha, and how type 2 errors are affected by sample size, the standard deviation, and the effect size. Generally, as the sample size increases, the power increases. As the standard deviation decreases, the power is going to as this is a typo. As the standard deviation increases, the power decreases. And as the effect size increases, the power increases. So a test is going to be better at detecting large differences than small differences, right? And if your populations have less deviation, then it's going to be easier to detect. If there's a lot of noise, it's going to be hard to detect those differences. So there's a typo here, but I'll correct it when I I'll try to correct it when I make the slide or the video. Now, so let's see. Study design often includes calculating a study size or a sample size such that the probability of rejecting a null hypothesis is acceptably large, typically between 0.8 and 0.9. It's important to have a precise estimate of an appropriate study size. So if you have a guess as far as like how big the effect size is and what the standard deviation is approximately, you can calculate the sample size that you would need to have a good chance of rejecting the null hypothesis, if indeed the null hypothesis is false. And so you don't want your sample size to be too big, because that's expensive. And so you want that, like finding the right sample size, you can calculate what you want, and so that you don't have to make too large of a sample. Large studies can be complicated, they can be expensive, and it says here even unethical. And I guess it depends on the type of thing that's being studied. Here's an example of a study sample size question. Say a pharmaceutical company has developed a new drug to lower blood pressure. It's planning on a clinical trial to test its effectiveness. So if individuals whose systolic blood pressure is between a 140 and 180 will be recruited. All right. Based on previous studies, blood pressures from such individuals will be approximately normally distributed with a standard deviation of about 12. Participants will be randomly assigned to the new drug or to a placebo, and the company will measure the difference in mean blood pressure between the two groups. So we're going to have independent samples, right? These people are put into two groups. One group gets the treatment, the other gets a placebo. The company expects to receive FDA approval for the drug if there's evidence that the drug lowers blood pressure, on average by at least 3 millimeters, 3 mm Hg, more than the standard drug. So if the effect size, they want to be able to detect an effect size of 3 at least. So how large should the study be? If the company wants the power to be 0.80, all right? So what we'll do is we'll be able to calculate this power. We can use R to do this, but so here basically it just runs through the calculation. Given an effect size of 3, given a standard deviation of 12 in the population, and a certain significance level, and this power that's desired, we can calculate that if, like, we would estimate about 253, right? You round it up, 253 individuals would be necessary in our sample size in order to have a power of 0.80. That is to say, to be able to correctly reject the null hypothesis if it's false. If a true difference really does exist, we would have an 80% chance of detecting that difference. All right, so now we're going to kind of extend these ideas of looking at population means to look at a multiple means of 3 or more populations, or 3 or more independent samples. So the kind of the simplest approach, which turns out to be not the best approach, would be to, if you have, say, 3 groups and you want to compare the means about each of these 3 groups, you can say, okay, let's pair up group 1 and 2. Let's do a T-test to detect if there's a significant difference in mean. We can compare up groups 2 and 3 and do the same test, and then we can group 1 and 3 and do the same thing. Now, in fact, this is going to be, so you roughly have to do, like, if you have like k groups, you'll have about k squared over 2 tests that are going to be needed to do. So if you have like 5 groups, there'll be 5 times 4 over 2. That'll be 20 T-tests that would be needed to be done. And the issue that you have is the more times you do a T-test, the higher the chances that you're going to be making a type 1 or type 2 error. And we're kind of concerned with making type 1 errors in particular. So, which is to say, like, if the null hypothesis is really true, and none of the groups have a different mean, every time you do a T-test, you're going to have about a 5% chance of getting the sample means different enough that you would reject the null hypothesis, a false positive. And so the more tests you do, the more likely it is that at least one of these false positives is going to pop up, right? So what we do is we don't resort straight to doing a bunch of paired T-tests. What we're going to, not paired data, but like pairwise T-tests. Instead, we use this method called Anova. It's a single hypothesis test, and it compares it looks at the variation around if you combine, it's like the idea is you combine all the data together and look at the variation around just the combined group mean, compare that to the kind of all the different groups and their variations around their individual means, and looks to see whether it's like whether the improvement, or whether it makes sense to put them into different groups based on the pros and cons of that. I guess that I don't want to get into the technicals right now. That's the gist of it, okay? So the setup is this. The null hypothesis is that all the groups have the exact same mean. So mu1 equals mu2 all the way up to mu k, whatever k happens to be. The alternative isn't that every single one of the means is different from each other. It's just that at least one of the means is different from the others. It could be that all of them are different, but the alternative is that at least one of them is different. So what we're going to be doing is we're looking at two quantities: the variability between the groups. How different are the group means from each other? In other words, how much does each group mean vary from the overall mean? And then we're going to be looking at, within each of these groups, we're looking at how much variability is the data within each of these groups. Okay, so this text is using MSG for the mean squared difference from the mean squared deviation between groups, and MSE is the mean squared. I guess E stands for error. Now the terms actually, these can be sort of, these are these are like measurements of variance. And so the test is ANOVA, which stands for analysis of variance. Okay, that's what the AN, O, and the VA are. AN from analysis, O from of, VA from variance. So here's an example. We've got, looks like we've got we have six different groups, and it looks like if you here they put them in blue and red. It looks like in blue we have groups 1, 2, and 3. It's hard. It's hard to see if these group means are different. But one thing we can see is there's a lot of variability within these groups. And groups 4, 5, and 6, these means seem to be different, because you can see the group 4 is lower, group 5 is higher, group 4 is lower. There's a lot less variability within each of these groups, right? The standard deviation, so to speak, is less. And so, well, let's get into we'll get into an example with and see. I want to go into example before we get into. Okay, we'll get into more detail then. The null hypothesis says there's no real difference between the groups. So if there's variation, it's just due to sampling chance. And in fact, then you could say the null hypothesis is really like all of these, even though you sampled from different groups, they're actually all part of one population. And then the variability between the group means should be the same as the variability within the groups. So the test statistic that we use for an Anova test is called an F statistic. I think F stands for fraction, meaning that this is a ratio of two variances. F is named after Fisher, not fraction. F is named after the statistician Fisher, but it turns out F is also a fraction. It's a ratio of two. So at any rate, the the distribution, the sampling distribution for the F statistic is, it's going to be, since the variance is a positive number, this ratio could be as low as 0, but it could go up to really big. And for us, if the population means are all about the same, the F statistic is going to be close to 1. When the population means differ, F will be larger than 1, and larger F values represent stronger evidence against the null distribution. So the bigger the F statistic, the more sure we can be that there is a real true difference in group means. The F statistic, the F distribution is a distribution that has 2 degrees of freedom, and these degrees of freedom come from formulas based on how many groups there are and how many observations there are within the groups. And then as the p-value, if the p-value is a right-tailed like a tail probability, for you find the F statistic in this F distribution, and you look at what's the probability out in the far right tail. So there's a few assumptions that are needed for an ANOVA, and one of them is to make sure that the observations are independent within the groups and between different groups. And that's going to be determined by really how is this experiment designed and carried out. Also, each group should be approximately normal, or at least if it's or a really large sample size. And we usually can look at graphically, we can look at a histogram or look at a QQ plot. These are some tools that we have to sort of assess normality of the data. And then finally, we need to make sure that the variability across groups is about equal. We don't want we don't want the ratio of the largest variance to the smallest variance to be more than 3 times. And that we can also assess kind of graphically. But we don't have hard and fast rules for these, but we kind of have like rules of thumb. I think that what you'll find is data is never perfectly normally distributed. So it's really about to what extent the data violates these assumptions, then we can be a little bit less and less comfortable with our conclusions from the Anova test. But as long as your data is pretty much normally distributed, and as long as your variances aren't that different from each other, we can be pretty cool with what the Anova test tells us. Here's an example of what QQ plots are. So a QQ plot, it pairs up each of the observed values, or observed the quantile for each of the values, with the theoretical quantiles from a normal distribution. So what we have is if your data is perfectly normally distributed, like in the third case, you're going to have a pretty good matchup of your points point by point. So you can see that the theoretical quantiles are almost the exact same as the true quantiles. The observed and the theoretical are almost the exact same. And the more deviation you have from a normal distribution, the more this plot is going to kind of deviate off of the line. As long as you don't have huge deviations, like in blue, it really goes under the line at the beginning quite a bit. And then that actually happens with the green as well. In green, actually, you're under at the beginning and over at the end, which means that you have thinner tails than you really should have. Generally, the QQ plot's tricky for small sample sizes, and you're never going to have lines like the dots perfectly on the line. And it takes practice to get good at interpreting a QQ plot. So sometimes you want to just look at a histogram and just make sure that it's not that skewed. But yeah, here's what a QQ plot for a skewed distribution would look like. And you can see that's very obviously going off of the diagonal, right? With a very severe skew. So anyway, After you do a Anova test, if you detect that there are a significant difference among the means, you then need to find out which of the means are different. And that's where we do these pairwise comparisons. We do pairwise T-tests. Now, like I said before, there's this risk that you are going to make type 1 errors. It's possible that these the population means are equal to each other, but because we're doing so many tests, that that you're just going to make a type 1 error. If you have an alpha at 0.05 and you're doing 20 different pairwise tests, and if in fact all of the population means are the same, 5% chance, you would expect on average to get about one, rejection, even though all of the means are the same. Because alpha at 0.05, every time you do a test, if the null hypothesis is true, there's actually a 5% chance that you reject it. Well, so one way to do this is to just lower the significance level for each test. The Bonferroni correction method, it lowers the significance level. It's pretty strict, but at least it makes sure that the total alpha isn't too big. There's other adjustment methods than R actually makes it easy to do these corrections. So it looks like we'll be exploring Anova testing in the lab as well to compare the non-dominant arm strength change, not by male-female, which is just two groups, but by genotype. When there's multiple genotypes, we can compare that to see if there's actually a difference by genotype. Here is what these three groups look like. We've got 3 box plots, and you can see there's some differences, but there's quite a lot of overlap in the rectangular part, the box. And the medians are close to each other. So the Anova test is going to tell us whether there's a significant difference or not. So in this particular case, we would say, okay, the null hypothesis is that the 3 group means are all equal to each other. The mean for the CC genotype, the CT genotype, and the TT genotype are all equal. And the alternative is that at least one of them is not equal to the others. We don't know which one isn't. In the alternative, any one of them could be different from the others. The alternative hypothesis is agnostic about which mean is different. It just says at least one of them is different. So the way that you do an Anova test in R is it's this AOV function. It does the test. AOV function actually creates an Anova test result. It creates an Anova test object. And to actually see the results of it, you want to do a summary of the Anova object. So you do summary and then parentheses AOV. There's actually some other methods, some other functions that'll get you Anova results. Here's one. So you put in your variable that holds the data, and you do a squiggle to break it up or group it by some other vector. Some other variable. So here we're looking at the change in arm strength grouped by the genotypes. And so the results here, you can see that you've got it tells you a whole bunch of stuff. It gives you the mean squares, and so this 3522, that's the mean squared variability, or mean squared deviations. With this is between groups, and the residuals line, that's the mean squared, that 1090, that's the mean squared within the groups. And 3.231, that's the ratio of those two numbers. That's our F statistic. And the PR greater than F, that's our right-tailed probability. That's our p-value. So here the p-value is 0.0402. That's a little bit less than 0.05. R puts a little asterisk next to it to show that it's significant at 0.05. And it'll put more stars depending on how significant it is. Yeah, so we would conclude that at least one of the group means is different. And this is at the population level, right? Obviously, the sample means are different, but we're making a conclusion about the populations that the sample is drawn from. Now, if the F-test is significant, then we should do pairwise comparisons. Each test is going to be done using a corrected significance level, not alpha, but alpha star, so that the overall type 1 error doesn't exceed alpha, the 0.05. Now these are sometimes called post hoc tests. Let's see. So these tests are done under the assumption that the variance between the groups is equal. So the test statistic is calculated using a pooled estimate of standard deviation rather than unpooled. This is a technical thing, and it's not so important we need to focus a lot of attention on, but just to know that the standard error, like what we looked at earlier, that calculation of standard error was using unpooled variances. So for pooled variances, it's a slightly different calculation. At any rate, we'll be going through this and looking at different ways of doing these post hoc tests in our lab. So if you use a Bonferroni correction, you would use 0.0167 because what you have is 3 tests we'll be doing. So we divide the 0.05 by 3 so that the total type 1 error is going to be controlled. Now this is a very loose way of controlling it. It's very simple and it's kind of oversimple. And there's some better ways to do it, but still, it's fine for our first time doing this. Doing the pairwise T-test is easy in R. So we are going to say, here's our data. It's in the ndrm.ch variable, and we have our grouping variable, and then we say how we're going to be adjusting the p-value. And here we're doing no adjustment to the p-values. We're just going to be using our alpha star. We'll be looking at these p-values and using alpha star. Now, there's ways to adjust the p-value so you could then have all of these p-values adjusted so that you compare them all to 0.05. But we're not doing any adjustment method. So we're going to compare these p-values that we get to our adjusted alpha of 0.0167. We did our own adjusting. And look at these, you can see that between CC and CT, that's a pretty high p-value. Between CT and TT, that's 0.144, that's also pretty high. But between CC and TT, it looks like that difference in means, 0.011, that's actually a significant difference in means. So this is what I was just saying, if you put in a Bonferroni adjustment, what it actually does is it is going to multiply the p-values calculated by the Bonferroni adjustment so that you can then just compare them all to the 0.05. So you can R can do all of the work for you. That's really the moral here. I think that's all I want to cover in this lecture. In lab, we'll explore how you can run into when you are comparing multiple like lots and lots of different means, lots of different group means, how you really can get quite a lot of type 1 errors. And actually, just generally, this is something that can happen when you have a ton of data. This is an issue with nowadays. We have a lot of data. With a ton of data available just in the world, you can do all sorts of comparisons. And when there's no real, true, interesting thing happening within the populations, just false positives will pop up now and then. There's a great example that's been done by looking at all these spurious correlations between completely unrelated things in the world. And the thing is, if you take 100 or 1,000 different variables that are completely independent of each other, have nothing to do with each other, but you just start comparing them to each other pair by pair by pair by pair, eventually you're going to stumble onto some false positives, right? And you can't be like, oh, look, there we go. So false positives are handled by, doing repeated experiments to see if the results are repeatable or not, right? These are the kinds of things that are done to make sure that the science is sound. Anyway, I don't want to go into the details in the next batch of slides because we'll be going through that stuff in lab. I think that's all I want to talk about with respect to inference on quantitative variables. So hopefully this will make a lot more sense as we go through the stuff in lab.